In the last video, we started talking about molecules and how to represent molecules, what makes molecules different from atoms. We're going to continue with that theme here, talking about a few different ways of representing molecules, a few different ways of writing the formulas for molecules. So we have on this screen here, we have four different I guess you could call them methods, four different styles, if you will, of writing a chemical formula. There is the most simple one. It's the one here on the left. And all this tells you is what you have and how much of it. It tells you, for example, in this case, you have 1 carbon and 4 hydrogens. But it doesn't tell you anything about how the atoms are connected together. Structural formulas, which are the next one, do give you that information. They tell you that not only do you have 1 carbon and 4 hydrogens, but all the hydrogens are attached to the carbon. So it gives you essentially a little bit more information. And the same thing is true for the next one here. This is what we call the ball and stick model. This one requires a little bit of analysis because they don't have the letters here. Instead, they just have balls that represent the different atoms. And so the color code is shown here on the left side of the screen. The black ones are carbon, white ones are hydrogen, and then the other two most common ones would be the nitrogen and the oxygen with blue and red. Chlorine is kind of sort of common as well, but those are these four are for sure the most common ones that you'll see. And so this structure, or this way of representing the structure, gives you even a little bit more information, because not only does it show you how things are connected together, it shows you in 3 dimensions how everything is connected together. Here everything is in 2D, and here we have 3 dimensions. So it gives you an even more accurate view of what the molecule would look like. And then the last one here, which is called space filling, is actually technically the most accurate of the 4, because molecules are not actually made of atoms stuck together with little sticks. They are more like blobs of electron density that are stuck together. And so this is technically, this is technically more accurate than this one, but I actually prefer the ball and stick model just because it's, in my mind, it's easier to see what is connected and how they are connected in the ball and stick model than it is in the space filling. So you might see these throughout the book. I just wanted to insert this in here really quickly so that if you do see these different kinds of structures, you're not just left out in the cold, essentially not knowing what you're looking at. Alright, let's talk about categorizing compounds. So in chapter 3, I want to say, we talked about categorizing all of matter, and one of the larger categories that we could put things into was the category of a pure substance. And we're going to take a closer look at pure substances here. So we said that you could have a pure substance, and we split that out into 2 smaller subcategories. We said we could have elements, which would be a single thing from the periodic table, and we also said that you could have compounds. And compounds are combinations of things from the periodic table. Those 2 subcategories, we're going to go ahead and split those into their own 2 subcategories. So elements, they're things where we just have one thing from the periodic table, but we could split that up and say that we have what's called atomic elements. These are elements where the simplest form of the element is a single atom. Now, the vast majority of the periodic table is made up of atomic elements. In fact, all but 7 of the elements on the periodic table are atomic elements, where the simplest form of the element that you can find is just a single atom. But there are some, again 7 to be specific, 7 elements from the periodic table that actually do not exist in their simplest form as a single atom. They actually exist as what we call diatomic elements. And I believe, yeah, so this is just kind of saying what I just said. Some elements exist as a pair of atoms, and there we go. There are the 7. These are the 7 diatomic elements. The nice thing about these is that it's fairly easy to remember which ones are the diatomic elements if you can remember that there are 7 of them, that hydrogen is one of them up here all on its own in the left corner there. But then if you can remember that the elements make a 7, you know, roughly speaking, it's not a perfect 7 there, but you can kind of see how it looks like a 7. Starting with the nitrogen, work your way over to fluorine, and down to iodine. So they're all together there with the exception of the hydrogen. So it's fairly easy to remember these, which is nice. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, along with hydrogen, all 7 of those do not exist in nature as just a single atom. They're either going to be diatomic, so you might find O2 or F2, or you could find them as part of a molecule, so you could find it bonded to something else. But if it's just oxygen, it's going to be O2. If you only have fluorine in your sample, it's going to be F2. These only exist in their pure, non-bonded to other elements form. They only exist as diatomic elements. And I do expect you to remember these 7. But like I said, it's fairly easy to remember these if you can remember they make a little 7 there. So you start, funny enough, with number 7, work your way over to fluorine, and then down, and then you have hydrogen up there in the corner. Right. On the other side there of the little flow chart, we have the compounds. We can split compounds up into 2 groups as well. So compounds can either be molecular, or they can be ionic. So molecular compounds, these are compounds that are formed by 2 or more nonmetals. And they can only have nonmetals in the molecule. So again, the nonmetals are the ones up here in the top right corner, again with the exception of hydrogen. Hydrogen's kind of a weird one, because in some situations it fits better on the left side of the table, but then in other situations like this one, it fits better over here. And I've actually seen a few odd periodic tables that has hydrogen in both places, which is a little bit weird, but at the same time it kind of makes sense. But anyway, molecular compounds are also sometimes called covalent compounds because they come together using covalent bonds, which we'll talk more about later. But the key thing for now is just to remember that molecular compounds are always made up of 2 or more non-metals. There will be no metals in these molecules. Ionic compounds, on the other hand, are always going to be made of a metal and a nonmetal. You will always have both a metal and a nonmetal. The metal is going to be the cation in the ionic compound, and the nonmetal will be the anion in the compound. And you will always have both. The formula unit for these ionic compounds is going to be a little bit different than what you would normally see for a molecular compound. Normally for a molecular compound like water, for example, the structure that you would write, the molecular structure that you have here, the chemical formula, that describes a molecule. But with ionic compounds, there isn't really a molecule to look at, because ionic compounds are made up of what we call a crystal lattice. You have a whole bunch of cations and a whole bunch of anions that are all just packed together. And all ionic compounds are this way. They're just kind of all packed together. There's not really a way that you can say, this is the molecule, because you could just as easily say, no, all of this is the molecule. Like there's not really a defined molecular shape or molecular structure. And so what scientists have just agreed is that we're going to take the simplest formula that describes the whole structure, and that will be the structure for the compound. So sodium chloride, for example, the simplest structure that could describe the whole thing is just NaCl. For every one sodium, there is one chlorine. And so because that is the simplest way to write it, that is the structure. You could make the argument that, well, that's, there's lots and lots of sodiums and lots of chlorines, but at that point there's an infinite, nearly, number of possible structures that you could write down. So we just say we'll take the simplest one, the smallest unit that describes the whole lattice. All right, so let's take a look at a few examples here. This is example 5.4. It asks us to classify each substance as an atomic element, molecular compound, or ionic compound. So we have 5 different things here. I would like you to take a look at those 5 and see if you can figure out what the proper classification would be for each of those. So go ahead and pause the video and give that a try. Okay. Part A, krypton. This is an element from the periodic table, and it is not one of the 7 diatomic elements. And so this would be an atomic element. COCl2, this is obviously a molecule because we have more than one element present. Cobalt is a metal. Chlorine is a nonmetal. So this is an ionic compound. Remember, metals and nonmetals, that's what makes an ionic compound. Nitrogen is something off of the periodic table, and it is one of the 7 diatomic elements. And so this is a molecular element. So it would be helpful if I spelled it correctly. Element. SO2, otherwise known as sulfur dioxide. Sulfur is a nonmetal. Oxygen is a nonmetal. So this would be a molecular compound. And then the last one here, we have nitrogen and oxygen, which are both non-metals, but potassium is a metal. And so this would also be an ionic compound. So there we go. Alright, I think we'll call it there for this video. In the next one, we will talk about determining the correct formula for an ionic compound if all we know is what atoms are participating in the or are present in the ionic compound. And then if we have the time, we might get into nomenclature. We'll see if we can get that far. So I'll see you there.